about what makes systems scale. And I don't peddle any products, so I won't be doing any of that. But what I will be sharing with you is experience I've had over the last 20 years trying to build systems that scale effectively. I'm going to go into it, and the perspective I've kind of learned, because I've actually run my own company, I've put my own money into it and lost it, and it gives you a very different perspective on how you just play with technology for what you want to do. So we're not just going to go and build rows and rows of boxes with things in them. What's more interesting to me is how you do something like this. How do you start with like a small corner shop and turn it into the largest shopping mall in Europe? I used to work next to this shopping mall in London. And what's really behind it is it's all about cost. It's not actually a technology problem, it's much more a cost problem. And I want to talk a lot about how the costs filter through the technology. So what does it mean to scale? Well, if you look at the axis on this, we want to look at volume. Now, volume can be units of work, transactions, amount of data processed, whatever you want it to be, but you want to increase volume. Well, as you increase volume, what you want to happen is not have your costs go through the roof, because that is not scaling. Scaling is where whenever you increase your volumes, you keep your costs reasonable. So the red line, this is probably bad, but it's probably bad for certain volumes. So if you're just doing a small scale thing, like I'll use another analogy, is like forget the shopping for a second, imagine building a bridge. If I want to build a bridge that goes across a little stream at the bottom of my garden, a little bit of wood is probably fine, although wood is not going to scale to go across a great expanse between two islands. And I'll use different things. So that might be fine, but it won't scale up. But when we start looking at proper scale, true scalability, people will talk about in the linear sense, is like the blue line. But I'd actually argue from a commercial point of view, that's not very good. If your volumes are going up and your costs are kind of going up almost equally in step, yeah, it's okay, but you should be getting economies of scale. So you want to be looking more at the green line as you're going up. And so when you start thinking about stuff and talking about scale, cost is so important. And you got to look at what are the costs that make up what you do. So what makes up costs? Well, it comes down to typically two things. There's fixed costs and there's variable costs. And fixed costs are the things that you must sink. And it could be like development effort up front. It could be buying kit and putting it in a data center. It might be building that data center itself. But before you take those jumps, you need to work with the business to understand what is the volume you're going to be dealing with. And it's a collaborative effort when we're dealing with this, because then you can work out, do I go for a variable cost model? Like, do I put this on Amazon EC2? Or do I actually build my own data center from scratch? If I've got no idea how many transactions I'm processing, I might as well just guess. So work with the business to work out what that's going to be. And be sort of aware that there are things like bulk discounts that you can do when you start purchasing at any sort of scale. So prepare for that and think about it in the future. So kind of typical question I would ask of anyone is, if you add another node to your system, how many more units of work or transactions or whatever do you get out of that? Unfortunately, when I go into work with many people, this is almost the response I get, no one has a clue. If you don't actually know how many units of work can be done by a given node or part of your system, how do you even know how to scale? Well, you can just throw hardware at the problem, which is the thing that's thrown around our industry a lot. And I think it's a little bit of a shame, because it is just effectively like burning money. It's okay that it does cost a lot to develop stuff, but do you know if the cost of what it is to develop is actually greater or less than the cost of actually buying the hardware? If you know that, it's a very easy decision. If you don't know, it's not so easy. And well, how do we get to doing some of this? So I'm going to just jump into the meat of this, which I'm going to go through 8 guidelines that I kind of know of and apply quite often when I'm working on projects to get them to scale. They're not set in stone, they're not rules. I don't believe there's rules in anything, but let's go into the guidelines and what's important. So first up, I'm a great believer in that the model for the business should be at the core of what you do. And this may seem strange in a scalability talk, but I think this is absolutely critical. If you're going to build anything for a business, start off with the core model. Great work for the likes of Eric Evans, domain-driven design, what Alistair Cockburn's been doing on hexagonal architectures. It's all about get the pure application at the center, keep it free from all sorts of infrastructure. Build that and measure that on its own. Can that scale and that work independent of all the other things that we wrap around it? And you'll probably find that it can, and you'll probably find that you can get really good, clean code by taking that sort of approach. Well, in the hexagonal architecture approach, well, how do I then persist that? Well, you provide an adapter that persists it out. That's one of the design approaches in that. I'm not going to go into detail about how to do that, but also Eric Evans talks about using repository designs for how you persist stuff, and that way you can get around the persistence side. Well, how do I get data coming in? You're going to layer things, and you're going to have adapters and channels that bring the data into you. So if you think, let's get the core model together, let's test it, let's make sure it works correctly. It is what the business require. I can then feed it with data, and then I can save it safely. I can then work out what are all of the characteristics to make that scale. But it's important to get that core model correct. And don't infect it with infrastructure for how do I save something, how do I do something. So I'm probably going to be a bit of a heretic. If somebody starts saying, use an ORM, I just run away screaming, because you're just mixing concerns at that point, and you're going to really struggle with scaling because you've just limited all of your options. If you have a pure, clean model, and then you have, I say, a repository pattern that you can choose to store it in some way, you can then choose to swap your storage however you want to do that, and you've got those options. And that way you can work and scale your system. So I mentioned we need a performance test and profile. I think this is absolutely critical. How many people here run a profiler at least even once a week? Very, very few. How do you know what your code even does? How do you get a feel for what it's going to perform like? To understanding it. There's a great quote back from one of the Microsoft press a while ago saying that if you're going to develop systems, you should always walk through it in a debugger. And it's something I took on. I found it was very, very valuable. Write your code, write your tests, write your code, run your tests, step through it in a debugger. It's amazing the things you see. It gives you a whole reinforced picture of the model and how it works. Same thing happens with a profiler. You start to understand the characteristics of your system. You develop a much better relationship with your system and just understand and get a feel for it. But writing good performance tests is hard. I find that the common problem that most people do with their performance tests is they'll write their system, run their performance test, and say, my system's not fast enough. More often than not, I've found the performance issue is actually in the tests rather than in the target code. So how do you address that? Well, first thing, do test-first development, and this really matters is even more for performance tests than it does for a normal unit test, is you write it against a blank, something that just returns straight away with a false answer, or even just a random answer, and then see if your performance test can run fast enough for what you want to do. Then plug in the real code, because you know at this stage whether your performance test is fast enough. If it's not, you know to go back and work on that. There's lots of common mistakes people will make. They'll also do things like only testing the same customer or the same product or the same entity of whatever type over and over again. What's going to happen? It's going to be hot and cache. It's not going to give you a realistic view of the real world. Well, how do you find that realistic view? Ideally, you take data from production. You should know your production characteristics and then have your tests influenced by that. If you're starting out and you're new, well, at least talk to your business people and find out what they are expecting the characteristics. You can guess, you can be wrong at that stage, but at least you're working off some sort of model that you can evolve and understand over time. What's really important, I find, especially when you start digging into something, you've got a performance problem, is theory of constraints. Quite often people will look at a profiler's output and they'll see the thing that's second or third going, I know how to deal with that easier than the number one problem. That's a very common thing. It's so easy just to be tempted into the thing you know how to deal with, the code you're comfortable with, the part of the system you're comfortable with. But actually the number one thing, if you fix it, you may find that 2 and 3 and 4 all just disappear because they were just an artifact of the first problem. So always fix the first and the largest problem that comes up, and you'll just find that the characteristics completely change after that. So it's a simple rule to apply, but that's one you should do. And human behavior, for whatever reason, people start picking the easier ones that they think are further down. Now, the fact that if we have performance tests, and we have all of this data, and we have realistic models, we can start making sensible economic decisions. for where to optimize. So like optimization being the root of all evil, there is a lot of truth in that. But there's a big difference between that, knowing the capabilities of your systems, and knowing what you want to achieve. So if you find you're 20, 30% off your target and you're going to be going live, you need to fix that at that point. Well, how do I fix that? Do I spend a bit more on hardware, or do I spend a bit of time actually optimizing the system? If I know the costs of adding another node to the system and I can roughly estimate the time I'm going to put into it, I can make that call. You may also factor into that risk. If it looks like it's going to be very complicated and risky to make those changes to the system, it might be much better to just add the node. But make sensible decisions based upon the economics and the risks that you're handling at that given stage. Algorithm behavior. This is a really interesting one. I see lots of people produce systems and their test case size going through a system is 1. And you think, really? Incredibly common. One of my first experiences going out consulting was back around 95, 96, one of the first internet banks. I've been doing a lot of work internally on products and started going outside to work and consultancy. And one of my first gigs, because I've been working on the performance stuff internally, was to go into this large bank who was having problems that whenever they switched on, it just kept crashing. And I went through, reviewed the code, reviewed the tests, and being quite young and naive at the time, I said to their board, "Did you test this with any more than one person?" And all their heads went down. And that's pretty much what had happened. And so this was the sort of dawn of the internet and people realizing the scale that can happen. They'd spent a lot of money on TV advertising campaigns, got huge loads come hit the system, and it just fell over and over again. And a lot of the flaws that they had made was they didn't know the algorithm behavior of their system. And they had some n squared and n cubed problems as load hit their system where the response time just went up a hockey stick. So they ended up with issues over here rather than nice order 1 things down here. So when we start looking at the behavior of your system, what is the behavior under certain loads and understanding those characteristics? Now, we can all go wide if we can get so much transactions per second out of a node, and if we've got no contention, which we'll talk about, that lets you go wide. But is that the answer in itself, especially when you're considering costs? It's how much transactions can we get through a node? So how do we improve that and make it better? And a lot of that quite often is dealing with the algorithms we're using and the orders of complexity that's in there. We need to understand the hardware that's under that, and I'll talk about that a little bit more. But one point I would sort of make now, it's not very well known, but I think a lot of the future as we go multi-core and we're dealing with large memory space is a thing called cache oblivious algorithms. It's a whole talk in its own right. I'd recommend anyone go and Google for that and look into it. It's really, really interesting. It's about how we have memory hierarchies and we have multi-core. How do we decompose those problems and chunk our way through them in a memory-friendly way to get at them? And it actually can work very well for many different problem sets on large data amounts. But the one killer that happens so often, and I'll bring it out as a special point, is unbounded queries. How often do you see on sites where people are allowed to give me all of the transactions I've done on my account, give me every unit of something that has been sold somewhere in the world? Those queries can just go on and on and on for a while. Where they start getting spectacularly bad is if there's a nested query in that. So you query a lot of things, and then based on the results of that, you're querying again. You can end up with huge problems. So how do you solve that? Well, let's bound our queries so that any unit of work has a maximum upper bound. And so I only want to bring back 100 rows if I'm going to go to a database, for example, or just even querying anything in the system, bound the amount so you deal with it in manageable chunks that can be amortized and costed up. And then that way we can start working out how our algorithms scale and what are the chunks of work that are actually going through those. I mentioned contention. This is the biggest killer when it comes to scalability, and it happens in the large and the small. What's really interesting is the techniques used to manage scalability or contention are often the biggest cause of contention themselves within the system. Locks being an example. Quite often you'll see small chunks of work that really only are a few hundred or a few thousand processor cycles to do, but they're surrounded with a lock, and it's contended, and that lock is probably adding many millions of processor cycles as it does context switches to kernel to deal with it. So whenever you're dealing with stuff, you've got to look at what is the management overhead cost in what you're doing. And once you've got any contention points, you get huge queues behind them, and that's what's going to cause the scalability. So the key to a shared nothing architecture is have no contention points. So don't have the single database that everything goes to. Don't have the single load balancer that everything goes through, because there's always going to be a contention point. And it's the same with getting to your data itself. Now, kind of for anyone who's actually looked inside the code of the Disruptor, this was an interesting lesson for me, is that the Disruptor was sort of given birth out of the need to develop something that fought contention around locks and queues. And given the problem set that we had at LMAX, I found it worked really, really well. But now it's kind of exploded, and loads of people are using it in other ways, and often without as much control over the hardware as they had. So in the small, to how you use the Disruptor, you had to claim a slot, you put your data into the slot, and then you publish the fact that that data is available. Then the consumers can take it. Now, how you do that publishing process, it's got an internal thing called the cursor. The problem that was happening when you've got multiple threads putting in at the same time is the cursor becomes a point of contention. And it's the one weakness of anybody's been using the Disruptor with lots and lots of concurrent threads hitting it. Because as you claim, you then end up waiting for other people to move the cursor forward. And whereas it's a lock-free algorithm, it's not a wait-free algorithm. And again, it doesn't have a fixed cost for the number of steps to do with that. So there's been quite a lot of work since that to move that forward. And I'm going to be releasing some new queues later in the year through a different open source initiative that completely removes that issue, because what I've worked out how to do is how to take that contention point out. And I've got completely linear scalability now with doing that. The ideas of that is also feeding back into the Disruptor, and there's going to be a version 3 that's going to start dealing with those sort of issues as well. The kind of interesting things about picking up on some of that is we also improve lots of other things along the way. But it's about fighting the contention. So that's an example in the micro. We've had loads of other examples in the past with things like false sharing. So you don't even realize you're having contention. Memory is moved around in what's known as cache lines. And there's 64 bytes at a time. And you can find you've got two variables sitting in the same cache line with separate threads updating them. And your point of contention then is the memory subsystem moving those cache lines between different cores, so it can be hidden. That's the micro. Well, what's in the macro? Quite often you see is a shared database. This is a classic problem. And even worse, shared tables within those databases. How do you get rid of that problem? Well, if you put a service in front of the database and you only talk to it via that service, you've got lots of ways of now removing a lot of that contention. For example, you don't need to read into the database. The service can actually cache the data out of that. The service can be looking, well, how do I shard that out and eliminate the contention being across different products, users, entities, whatever it happens to be. So think about what are the contention points in your system and eliminate them. Many people will suggest use a load balancer as a way of scaling your system. It does give you certain characteristics, and they also did certain things at a point in time, and quite often things are moving forward. So a load balancer sits out in front of all your web servers and channels your traffic through. It typically does two useful things for you. It does many others, but two major ones. Quite often it's doing SSL offloads. So it's dealing with the encryption and having specialized hardware to do that. Ever since the Nehalem processor, which is nearly 4 years ago now, we've had support for cryptographic instructions inside modern processors, so we can be doing that local. If you're running OpenSSL on the latest versions of Linux, they're just automatically using that, and it's available to you. Other things it's doing is connection multiplexing. TCP stacks are getting better and better all of the time. So it's dealing with those problems, but it's now a point of contention. And it's also a point that has very different skills. And so your teams aren't scaling the same way as well. Because one of the ways to make your team scale the best is have very similar skills and very similar technologies that everybody can use. You've got a weird technology sitting over on the side. You've now got a contention point in how your team works, as well as a contention point in your architecture. And so avoiding specialized hardware, unless it's really, really giving you a big advantage, will also help scalability in your development efforts itself. Well then, how do I deal with a whole farm of servers, you may ask? Well, as part of the bootstrap process, as you connect, you can get a range of servers you can connect to, and your clients can then just choose. And all of a sudden, you've now got a problem that federates up and scales up much, much better. And so I think it's really valid exercise to just walk your architecture kind of end to end and see, do I have single points of contention? And then as you apply load with your load test and you start profiling, those hotspots will soon start to light up. And you'll start seeing if they're an issue or they're not. So getting them out. Well, how do we often get hotspots like that out of our system? Well, one of the ways we usually do it is put a queue in front of it rather than have things bang on it. And Little's law is a beautiful little piece of mathematics, incredibly simple and well worth sort of exploring and understanding. But a simple way to think about it is if any execution unit, be a thread, a process, a node of some description, takes a period of time, say that period of time is X, to do a piece of work on average, and you have a queue in front of it, and if your queue has got 10 items in it, the last item is going to have to wait 10x before it actually gets its work complete. And so you can start predicting the response times of your systems. And having the queues around is kind of interesting, but most people quite often don't think about queues in their system, yet queues are everywhere. Whether you realize it or not, queues are there. I would say embrace them and just deal with the issues that come with them and also understand them and get the benefits. So you say, why do I say queues are everywhere? Well, let's say I'm not going to put a queue in front of something, but I'm going to put a lock around it. What do you think happens when multiple threads go to access the same thing that's protected by a lock? One gets it, the others all stop. They're put onto a queue by the operating system to be scheduled to run at a later stage and woken up at a huge cost. Leaving your process address space, having your caches polluted, having to be woke up and rescheduled, maybe scheduled again on a different core at a later stage. This is all very expensive, and in the meantime, making no progress. Take the other approach. Let's say your system's asynchronous and you've got a queue. Is you hand the piece of work over to the queue to get done, you go off and do something else. You're busy, you're useful, you're going to be scheduled in the same place, and you have a thread the other side doing the piece of work. So here's a typical system that you'll see. You typically have gateways dealing with the outside world and your customers, and you typically have some sort of transaction service. Grossly simplified. There could be many more layers, many more ways of splitting that out. But we usually have a network stack with a pool of threads taking things in. Those pieces of work, typically at the gateways, you're applying border security, protocol translation, turn it into something useful you're going to do internally. So it goes on to a network stack again to arrive over at your transaction service where you do your piece of work, whatever that happens to be, which may end up updating storage. But whether you model these queues or not, they're going to exist. As you go to write to your network, you're going to be queuing. As you're going to read from the network, you're going to be queuing. If you've got a thread pool here, as you go to submit jobs to it, you're going to queue. I'm a great believer in bring those queues out so you can see them. Once you can see them and you're managing them, you can start doing interesting things. First, really important thing is bound them. If you put a lock in front of something and it's got no bound, what can happen is the queue can grow and just keep growing and growing and growing indefinitely. Now, the problem most people will probably see is their system blows up with out of memory error, but the problem happens way before that. That's just the final cause. It's like having a nasty disease and then dying of pneumonia. It's actually the nasty disease that got you in the first thing you want to watch out about. And the nasty disease here is your cache overruns. So as you're adding things to a queue, so I've got a queue and it's building up, and so it's chugging along, it's getting bigger and bigger. Sooner or later, that queue doesn't fit in your cache. Then what happens is, as you're removing in a last in, first out manner, first in, first out manner, the thing that's going to be picked up by the consumer has been sitting so long, it's actually been evicted out of your cache. And so your consumer that isn't catching up now is getting cache misses, and the world has got even worse. Very quickly then it slows down even more, and then the queue just grows at a rapid rate, filling memory, and the whole world is not so good anymore. Better thing to do is keep your queue bounded. Because then also you can honor a response time characteristic, because you also don't want to give that horrible response time experience to end users. So I want to say, I want to keep my response time within a given bound. I can work that out given Little's law, given the queue size, what it should be. Now what happens when my queue fills? What you should do then is apply back pressure. So you don't accept any more units of work and you apply back pressure back. So in this case, let's say the storage system isn't keeping up and this thread's trying to write. Well, if it's blocking at this stage, that's fine, because this queue then is going to back up. Now if this queue backs up, it's going to fill, and then this thread is not going to be able to dequeue any more network packets. So it's going to put back pressure to here, which means that this thread can no longer enqueue any more network packets, which then fills that queue, which stalls these threads, which eventually stops consuming from the network, which eventually stops no new work coming into the system. That's a better experience for end users, to keep processing and deny new input rather than just have your system crash. Because at least you're still offering service. You're offering good service up to your maximum capacity. I like the analogy of I'm running a coffee shop or something. I'll only allow in so many people, and then at that point, I'll say, come back later, please. Now, what's come back later, please, in this? Well, it could be a message to the user like a 503 and a HTTP response saying, server's busy, come back again later. But at least everybody who's in there is getting a good experience, and it's all working. Now, in fact, if we've got all of these queues and we know the average time it takes to process something, we can actually work out really interesting things like, what is the average response time a user is actually getting in the system? How many transactions per second are we dealing with? Is the rate of which things are going through queues? So making them first-class concepts gives you a lot of insight into what your system's doing and bringing them out. Also makes things nicely decoupled and easy to model and test. And so if I want to just load test this lot as an individual component, well, I can just throw in and out of these two queues. Works really nicely. And that way I can get faster feedback cycles, because we all know that one of the most important things with agile or lean methodologies is fast feedback cycles. Apply it at all levels of what you work at. So I can get much faster feedback cycles if I just have to run tests over and over on this rather than end to end, once I've isolated the problem. But I can also test end to end as well. But I've got the choices. I've got the ability to do this now in and out. I can also sample things going through. I can add tracers and different things to know what's going on. It's so important to know what's going on in your production systems when you want to work out if you need to scale. And then you can start taking this data for things like capacity planning. Because capacity planning, quite often people will look at, well, what's the memory utilization, what's the CPU utilization, what's their I/O utilization. These are useful things, but they're not enough. It's actually even more powerful the further you come up the stack, because that's what's really telling about everything else that's underneath. If you're finding your response times and your queues are filling up, you know you've got an underlying problem much, much quicker, and you can deal with it. So, kind of interesting one on this. This is a problem I'm seeing over and over again, and I kind of call it the curse of logging libraries. Little's law, great example of how queuing theory works. Amdahl's law, another great description of how parallel computing can work and what is the parallel limiting component. I spend a lot of my time helping people scale systems, and one of the biggest problems is usually logging. Happens over and over again. It's usually one of the biggest limiting factors. And so I've spent a lot of time looking inside most of the common logging frameworks, sort of log4j, log24j, logbag. Doesn't matter if you put SLF in front of it, the built-in JDK logger, all of the various ones. They all pretty much do the same thing internally. And they are a perfect exercise in how to screw up systems design and disregard Little's law and Amdahl's law. By changing how we do logging, massive changes can happen in our systems. And this is one of the open source projects I'm currently tackling, because logging uncontended, single thread, with nothing else going on in the system through the normal JDK logger takes 16 microseconds on a very fast processor with an SSD underneath it on average. That is horrendous. 16 microseconds. You add 2 threads to it, you're up to 35 microseconds on average. It's not even getting cost of scale. It's getting worse. You start adding 8 threads, and you're way into the hundreds of microseconds. And they're all queuing up to basically log. And then you get all sorts of really nasty characteristics. So if you're the unlucky thread that fills the buffer, then has to be flushed down to disk, everything else is behind it because the whole thing's rocked with a lock. You get the sawtooth of latency, and everybody behind it suffers in the tail. You reach the end of the log and you need to roll it. Guess what happens? Everybody in the queue suffers again in how it happens. Really simple design approaches can fix this and we can get much better. But it is the perfect anti-pattern to how to build a scalable system. Just look inside what loggers do and do the opposite and you'll probably do better. But the thing is, we need to log. It's important. It should become a first-class concept and we should bring it up to the top. Like I've even seen systems whereby people have protected their code with is debug enabled around them. I've run a profiler and found out, in many cases, 18% of total CPU time was spent calling is debug enabled. It's crazy. Let's get better. So, what's one great way of eliminating contention in our systems? Well, separating reading and writing is a really, really useful thing. Because so often we'll put a great big lock or a management system to avoid contention around our core data, our core model that we want to read or write to. Those reads should not be impacting the writes that are going on, yet so often they are. So if we can separate them, we can have both sets of traffic flowing completely freely. Well, how can we do that? A really good technique I've found is using event sourcing and CQRS. Command query responsibility segregation. And what we do with that is the changes that are happening to one model, we have a stream of events that go elsewhere. And we can rebuild that model many, many times over and over again. And I think about back when I said, let's build a model completely independent of all the infrastructure that's not tangled into it. Now we have a model we can run anywhere. If we put the same stream of events into that model, we can rebuild it. All those models can answer loads and loads of different queries, as many as we want in a very, very scalable fashion. And even if we get down to the stage, well, how do I get the data to all of those? If you want to take that step, there's multicast and all sorts of other means of getting data out very fast to many different ways. So we've now separated reads and writes. Writes are still an interesting problem. Well, one of the biggest issues with writes is if you're actually doing updates or replacements. And I think the world is starting to realize now that doing updates in place is a very difficult thing to get right and get the concurrency right on. It's much easier to have worm-style storage where data is immutable and you create a new version. Like Datomic is a good example of this. Is data is effectively facts. Like where I live now is the property of my address and the time. Now, if I move house, my old address is still completely valid. Why do I want to update my address field? I should be writing a new address with a new date from which I started at. So when I want to query where do I currently live, I want to look at what is the current address that hasn't been superseded by another address. Now, by having those sort of append-only style structures, it's so much easier to start dealing with the concurrency issues. Like if you go down to, like, say, a database, I know MySQL and Oracle very well, and I know many other databases have similar characteristics, and a lot of the new column stores and NoSQL databases are doing this as well. If you write append only, you can get much, much better throughput. So in Oracle, you can hint a query to be append only, and so when you're doing an insert, and what it doesn't do is it doesn't try to find space within the table. It goes right to the end to the high watermark and writes after that. Now, if it's writing after the high watermark on a table, any queries that are currently running will always get a read consistent view, so it doesn't interfere with running queries. MySQL can do exactly the same thing. So thinking in those sort of append-only immutable structures works incredibly well. It also works incredibly well when you look at the underlying hardware that it's running on. Disks do very well sequentially. Spinning disk can read and write phenomenal amounts of data sequentially. And so that's kind of great, and you're adding them. SSDs have got a lot more performance, but also they have issues with updates. SSDs give you completely random read access. When it comes to write, if you overwrite part of a file that's currently there, it has to actually mark that data as to be garbage collected. It then allocates space elsewhere and writes that data in. And because the way they work is you can read and write a 4K page at a time, but if you want to erase something, you've got to erase a whole block because they're organized into an array. And the blocks are 2 megabytes in size. So if you're going around modifying all of the time, you very quickly wear out an SSD. Whereas if you just write append only, they go through really fast, really friendly, and you don't even have all that GC cycles going on hurting you in the background. So that's append only. Also important to cache. Caching is the way to get at anything quite quickly. And so stuff that's really, really important to cache. Also tell a story of a client I had earlier this year who had an incredibly peaky problem. They were selling things online, and most of the traffic happened on a Sunday night or around holidays. The rest of the time it was really, really quiet. And to deal with this problem, they started throwing technology at it. I think this is the disease of many developers that I call CV-driven development. So they started off with they had Python, it kind of worked, it needed to scale. They had Postgres in the back end to store their data in. They then moved from that, well, let's put Memcache in front of it, and that deals with a little bit of the problem. Well, the work started getting really, really complicated, so let's put this work out to a farm and install GUnicorn. Well, GUnicorn couldn't work so well with Memcache, so they installed Redis. And so all the data starts getting copied around all of this different things, and this was getting bigger and bigger and bigger and more complex. And I just sat down on a quick calculation and realized all of the reference data for their catalog fitted into a few hundred megabytes. No one had sat down and done that calculation. And so get rid of all of this technology, read it out of Postgres whenever you start, and just cache it in all of the nodes. It hardly ever changed. And what they did do is they used Memcache then as just a way of coordinating between the nodes, where the nodes would poll occasionally, and there's just a flag set in Memcache to say whether you needed to re-pull your cache out, because it happened so infrequently, and they were able to run off that. System went a whole lot faster, and also scaled perfectly because they just all read out to this. They're adding a new node on peak, so we end up running an elastic cluster, whereby whenever the peaks happen, you just spun up new nodes, they just read out the cache data, and they could just all handle the requests. Absolutely no problem. So just sort of thinking about that, don't get hung up on technology, just go back and be simple. And the simple stuff works really well. As I mentioned, fact-based data works really well as well, because you don't have to invalidate that. You don't have to invalidate a cache when you're dealing with fact-based data. At any given point in time, that fact is valid. At a later point in time, another fact is valid, but you don't need to delete that old data. We have so much memory, so much storage now. Take those sorts of approaches, you can eventually garbage collect and purge if that's an issue. It's so easy to drop a table, truncate a table, whatever. Updating individual rows is incredibly expensive. And also for many business problems, quite often perfect is not the right answer. You go through a booking process, you can read availability on hotel rooms, you can read availability on a flight, you can read availability on most things for logistics systems, and if the point you read it, there's like 100 or so things left, and even later, you don't need to reread again, just attempt the transaction, and at that point it can fail because availability is gone, in which case you can choose to update your cache. Don't try to keep perfect and up to date all the time. There's a lot of things we can play with. Like, mechanical sympathy is kind of one of my big passions. And it's kind of driven by just knowing the infrastructure and what you can get out of it. Whenever I started LMAX, I got in an old team that I had worked with, and they built part of our front end that was customer-facing as web traffic. And we run some profiling, we run the load tests on it, and it says, I'm really proud. We've got 800 requests a second per each node. That's just not good enough. And they're like, what do you mean? That's pretty good. That's as good as we see elsewhere. And they didn't see where I was coming from. I says, well, if I actually look at what's going on, the network stack, the whole infrastructure coming right up through the app server that we're happening to using, I know from previous measurements could handle on that hardware 37,000 requests a second. So 800, not actually that good, really. What he's doing with the rest of it, and then just run the profiler, we found a couple of hotspots, and we will fix them and put them right. But being aware of the capabilities of the platform that's underneath makes it really powerful for knowing what you're going to get out of it. I like to think of this just the same as like, if I was a structural engineer, I would be fired if I don't know the tensile strength of steel, the compression strength of concrete. If I'm going to start building stuff, you don't need to know how to go and make concrete. You don't need to know how to go and make a network card, but you should know what it gives you. You should know the characteristics of what it has. And so when it comes to things like writing those load tests and performance tests, I write them for the infrastructure as well, because I know what it is. Then I know if I update a driver, if I update a third-party component, and all of a sudden things have changed, I can find it, fast feedback cycles, and get it, and I know what's going on. And you can also then sensibly capacity plan for your software on top of it, so what it's going to do. I think it's also really important to know what happens when it breaks. So as you load test things to the point of breaking, does it fall apart? Or does it sort of follow a curve and then go, I just can't take anymore, and continues nice and flat? That's actually quite a nice user experience. Some things are designed very well that way. So as I talked earlier about queues and back pressure, if you design like that, you get that nice characteristic, you come up to maximum capacity, and you continue at maximum capacity, and you deny new requests, but everything else gets processed at the same rate. Much better than going, boom, bang, and falling off after a J-curve. You find that out by testing things to breaking point. So do it with your own code, do it with third-party components that's there. It's actually quite good fun. It's a really good way of firing up people in the team and giving them some fun, some passion in what they're doing, and they learn an awful lot. And your code and the systems all get so solid as a result of doing these type of things. A really interesting one I find kind of here at the bottom is when you get failures and you've got hot swap components, what's the behavior when the replica takes over? Because quite often people test failover in different scenarios, usually when there's no load in their system. It's really important to test those at the point of stress, because quite often find you get cascading failures in systems, and it's usually under extreme stress. So if you find something that overheats and the thermals cause a problem, it's usually when it's under extreme load. It's not going to happen whenever it's just sitting there idle, not doing very much. So I'm going to kind of finish with a very different sort of point, and that is about being commercial. I'm a great believer in you should understand the business you're working on, because if you understand the business, you understand the demands of that business. What are the characteristics to which your system is going to be used? If you get passionate about that and knowing about it, it just informs so many of your decisions so much better about how the systems should work, how your load tests should work, how different things work. And quite often I find people working with the business and often not working very, very well, or as well as they could be. And I've got a kind of golden rule with some of my teams is, in any interaction with the business, no matter what they ask for, no is not a valid answer. Because it's not. It's really unfair to ever just say no. You can say, yes, we can do it, and here's the consequences of doing that. Those consequences might be very difficult to deal with, but that's an informed, respectful conversation. Just saying no and pushing back gets you into a way of working with the business that you don't find out all of the things that you need to know, like what are the demands the system's going to put on you, what are going to happen next month, the month after, so you're kind of ready for dealing with that. So breaking down those barriers. There's some really simple things you can do to help building those relationships and getting them working right. Like a classic one is get your team leads to just make sure they go and have a regular coffee with their counterparts on the business side, understanding their problems, what they're facing, and making sure you're building great software that actually suits what they need. Eat together. It's a really primal thing. Seriously, it sounds so dumb. If you work and you go and get a sandwich and you come back to your desk and you don't even eat with your own team, never mind your extended team in the business, I find you've probably got quite a dysfunctional company that doesn't work anywhere near as well as a team that spend time together, care about each other, and just do some of the primal things like just having meals. When you do that, you quite often find informal structures grow that work really, really well for building that team sort of philosophy. And the best way to get something done is by influence rather than authority, and working through all of that. And especially on the non-functional side of things, you really need to do that in a kind of subtle way, because it's a give and take and no one really knows the right answer, so you've got to work together. So like, what is the load going to be at the end of this year? you need to work with the business. You need to know what they've got plans coming up on product promotion, on marketing, just what ideas they've got through the sales pipeline, and then you can start working on that together with them. I think kind of final point, that's key to getting this, is have fun. By actually doing a lot of this, doing the things like breaking the system, writing the tests, knowing how it's doing, getting the numbers up and graphing them, working with the business and having fun, it really helps improve it. And let people talk about them, because performance is a great thing that you can go and get public talks and stuff and all on. So getting people, I've worked out how to drive the Linux TCP stack to handle 1 million concurrent connections. Makes a great talk, but you learn so much doing that and you'll write much better systems as a result. So on that point, I'll finish and take questions.
Yes? You said that event sourcing makes things scalable as a one group responsibility separation. Now, with some disruptor folks, there was the argument that event sourcing makes things reproducible on a single thread, right? It takes on complexity out of stuff. Now, how, with that background, does it make it scale well? I mean, it's good for performance because you drive people to the next, but how does it make it?
Yeah, so it plays to the first point that I made, that we want to work out what is the economics per node. Whenever you're not having lots of management overhead, like lock contention and managing that, you can work out quite well what is the total number of units of work you can do per second or per cycle on your machine. So that gives you a really good metric. The thing you've got to mix in with that is the ability to shard. So if it's just the read style case, well, you just send the stream of events elsewhere and you see QRS. The right side, you have to shard. So you want to look at, well, how do I shard my data? Do I shard it by customer, by product, by deal type, whatever? There's usually one of those 3 dimensions. I had a friend of mine a few years ago coined the phrase of saying, everything in the business world breaks down to people, stuff, and deals. And you can usually shard by one of those dimensions. And it scales up nicely. How do we do logging? I write my own logging. And I find this to be a common thing. So quite often I'm fixing performance problems. Logging's usually one of the first things I end up fixing for people. So watch this space, and probably before the end of this year, there will be a new high-performance logging framework available. My goal is to have it completely low touch, sort of sub 100 nanoseconds cost for log message with no contention issues. But also be able to do nice things like, when we start running in clustered environments, especially virtualized, you typically don't have local storage, so you don't want to be trying to use traditional logging mechanisms at that stage. So having the ability to send logs back to a central aggregation point and deal with them efficiently, and deal with them in a very friendly way, because a lot of people who write loggers tend to have very little machine affinity or sympathy going on. So whenever I'm logging through large batches of data, I want to apply adaptive batching and smart batching to what's going on. So if I get a burst of traffic going through, well, underlying in things like, say, the Linux file system, I can use things like send file. So I can map, so say, memory map data that I've written a lot of data into across to a file for archiving, out onto a socket to send elsewhere. And those sort of things are going to start becoming available because everybody's just doing these sorts of things over and over again. In finance, virtually everybody I know ends up building a framework that does something like this, but it's happening elsewhere too. Anyone who's got significant volumes that can't use the traditional logging methods. Thank you very much.